So in this video, we're going to see some examples of linear time invariant systems. The contents, so we'll look at some examples of LTI systems, and then we will look at another kind of representation for discrete time systems, which is called linear constant coefficient difference equations. Okay, let's look at the first example for an LTI system. It is simply a time delay system. You have seen it before. And how does it look like? So you have yn is equal to x of n minus capital N. So basically you have an x of n, which is something like this. Let us say 0, 1. And your y of n is simply a delayed version of the same thing. Let us say your capital N. Okay, let us keep it general. n plus 1. Right, so this thing moves here, this thing moves here. So is it linear time invariant? Okay, how do we check for linearity first? So let us go to the basic definition of linearity. The basic definition of linearity is that any transformation of, so let us say we have two sequences, x1 of n and x2 of n. If I linearly add them with some weights, a1 and a2, which are scalars, could be real number, complex number, but given x2 n, so this transformation will be equal to a1 times t of transformation of x1 n plus a2 times transformation of x2 n. This is the basic definition of linearity, which we have seen in the previous videos. Let's apply this definition to this signal. So what will be transformation of x of what will be transformation of x of n? This thing is equal to y of, or this is y1 of n, but it is equal to x1 of n minus capital N, right? And this term will be likewise equal to x2 of n minus capital N. Let us see this side. So here our signal is simply x1. So if I take this signal and pass it through this system, it just introduces a delay. Basically it converts n to n minus capital N. So this will be equal to a1 times x1 n minus capital N plus a2 times x2 n minus capital N. So you can clearly see the left hand side is equal to right hand side. So hence we prove that this system is linear. So this system is indeed linear. Now let's look at the next property, time invariance. So what is the basic definition of time invariance? The transformation of a delayed version of a signal, let us say x of n minus some other n dash, a delayed version of a signal is equal to the transformation of the non-delayed version of the signal, which is x of n, but the sequence is shifted by n dash. This is for time invariance, this condition must hold. So let us see in our example, does this condition hold? So what will be time delay of this thing? This will be equal to x of whatever is the signal. You just have to add a delay of n, right? And here you have put n. So basically this thing doesn't play any role because you are taking the signal as it is, n minus n dash minus n. Let's see on this side what happens. So okay, I have to say this is the whole thing. The transformation of xn, this you know is x of n minus capital N, this sequence. And now you have to take the n minus n dash element of this sequence. So you just replace your n with n minus n dash. So what do you get? X of n minus n dash minus n, which is same as the left hand side. So this implies that yes, this system is indeed time invariant. Okay, now let's look at another property, which is causality. Is this system causal? We know the definition of causality, that our inputs, our output should depend only on the input which it has already seen. Basically, y of n should depend on x of n dash and n dash basically could be, or n dash could be a subset of whatever until n minus 1 comma n. That is it. So it should depend only on the past or the current inputs. It cannot depend on the future inputs. Does that happen here? It clearly happens here. If n is greater than 0, then it is a causal system. Right? Let's see some general rules of thumb. So to determine linearity, time invariance, and causality. So if my yn depends linearly on xn, then the system is linear for sure. For example, yn equal to xn square is not a linear system because it depends on the square of the input, and if you try to apply the basic rule, it will break down, right? Now the question is, okay, is this system a linear? Apply the basic rule and you'll find out that when you take sum of two signals and okay, let me write it down. If you take sum of two signals, then it will become x1 plus, or x1n plus x2n plus 1. On the other hand, if you apply individual signals, you will get x1 plus 1 plus x2 plus 1. So this is clearly not equal. So this system is not linear. Okay. Now let's see time invariance. How do you know if the system is time invariant? Generally, if it has no explicit dependence on n, then it is time invariant. Let us look at this example. Yn is n times xn. So if I shift xn, then this n won't change. So this system will be not time invariant. You can apply the basic rule and find it out for yourself. It's very straightforward. And then we have seen resampling example, that if you are resampling a signal, then basically downsampling, then it is not time invariant. Okay, for causality, how do we know a system is causal? For a system to be causal, our impulse response should be 0 for all n less than 0. Then the system is said to be causal. What is the meaning of impulse response? Then the input is an impulse function. What is the output? So when the input is an impulse function, what is the output? So it means that this input cannot influence the output at past times. It can only affect inputs at the future times. Then the system is causal. Okay, let's look at this same example, time delay system. What is the impulse response of this system? So how do you find out impulse response? Impulse response means just my input is an impulse. That is it. Xn is equal to delta of n. Then what will be my y of n? My y of n will be equal to simply delta of n minus capital N. And by definition, this is my h of n. Right? So my h of n is delta of n minus capital N. So you can now plot it. 0. So if n is greater than 0, then you see that your h of n is 0 for all n less than 0. This means it is a causal system. So, okay, so this is a way to find out impulse response of any system. Now let's look at another example of moving average system. So this is a moving average system. This is how it is defined. Is it LTI? So for linearity, what you find is your yn depends linearly on xn terms. There are no constant additions. So yes, it is linear indeed. And for time invariance, there is no explicit dependence on n. There is no resampling. So I can safely say it is time invariant system. What is the impulse response? So impulse response is very simple. Hn is equal to, okay, another way to write it is, which you already know, it's a transformation of delta n. Okay, to be more precise, I will say n because I'm writing it as h of n. Now, what is this? This is simply y of n when xn is delta n, which means 1 upon capital N summation k equal to 0 to n minus 1 delta n minus k. Very simple. Is it causal? Okay, let us plot it. If I plot it, I get this is my n. So let us say capital N is any number, positive number of course. So what is my h of n? H of n is, let us put k equal to 0, so delta n, which is 0. If I put k equal to 1, delta of n minus 1, which will be this thing, and so on up till capital N. Oh, sorry, capital N minus 1. Right? So this is my impulse, and then 0 everywhere else. Okay, this is my impulse response for this system, and I can clearly see the impulse response is 0 for all n less than 0, so it is causal, yes, because Hn equal to 0 for all n less than 0. Okay, now let's move to the next topic, which is linear constant coefficient difference equations. So basically these are difference equations where the constants, where the coefficients like an, ak and bm, they are constant. This is another way of representing the system. We have seen previously the ways to represent system is, okay, you have yn is equal to t of xn, right? And we have also seen another representation is, if it is an LTI system, then h of n is equal to something. That is another way of representing a system. You can represent systems with block diagrams also. That is another way. Okay, and this way you can clearly see, is the system linear time invariant? Yes, this is an LTI system. Okay, so what is the use of this kind of representation? The use is that it is very handy for implementing the system with block diagrams or with practical circuits. So remember the basic operations we have at hand. What are the basic operations? You remember scaling by a constant, summation, and multiplication, element-wise multiplication, and things like that. These were the basic operations we have at hand, and now I can design a system or construct a system using these basic operations if I have this equation. Let's look at one example to be more clear about it. Okay, first we will discuss the block diagram representation. So given this equation, how do I use basic blocks to construct such a system? So my yn is simply this. I can write it like this. I can assume a0 is equal to 1 without loss of generality, because I can divide everything with a0 and scale my coefficients, other coefficients. So now how do I represent such a system? Okay, let's start from this part. Okay, my yn is the output, and my x of n is the input. X of n is the input, and I'm multiplying this with a constant which is b of 0 in this case, and then it goes to sum. Okay, and what else do I need? I need x of, when m is equal to 0, that is done. When m is equal to 1, let us look at that part. So I have to add a delay here. So a delay function, a delay operation you have already seen. And this one goes to another scaling. And this scaling is b of 1. And it goes to, okay, the summation. Then I need x of n minus 2, which means I add another delay. And I again scale it with b2, another constant. And I add it. And in this way I can keep going until m, capital M. Right? And what I get in the output here is basically this term, the first term. But now I have to subtract this term as well. So how will I do that? So this means the output here is y of n. The output here is y of n. Now I need y of n minus 1 times ak. So I will take this y of n, I will apply it to a delay function, z inverse, and the output of this delay will be scaled by the term a of 1, and then, okay, or minus a of 1, and fed back to this summation. Right? And similarly, I have to now get y of n minus 2. So I will apply another delay function, z inverse. And the output is again scaled by minus a of 2. And again fed into the summation. And in this way I can keep going until n. So this is the way I can implement a system using linear constant coefficient difference equation representation. Okay, now let's look at one example. You can see an accumulator. What is an accumulator? Basically, your yn is simply x of n plus x of n minus 1 plus so on up till infinity, which means all the terms. So this is, if you want to implement this system, it will need infinite number of summations, right? You have to, the number of delay functions which you need, that will be enormously large, and you don't know how many you need, because as your capital N, as your n is increasing, you have more and more values to save. So it is practically not possible to implement such a system. So what do we do in such a case? We use LCCD representation, linear constant coefficient difference equation representation. So I have to just rewrite my equation like this. My y of n is equal to summation k equal to minus infinity to, let us say, n minus 1 x of k plus x of n. Right? I have just opened up the summation and written it outside. But what is this term? You know this is y of n minus 1. And this is an accumulator system which you very well know how to implement using LCCD representation. This is the LCCD representation. How you implement it? It's very simple. You just need to add one delay term, which is, this is y of n minus 1, right? And that is it. So you are adding x of n and y of n minus 1 and you get yn. So this was the LCCD presentation, and this is how you implement an accumulator. Thank you.